The universe has always looked chaotic to us, a vast field of collisions, drifting rocks, and silent stars. But what if it isn't chaos at all? What if it's something far more organized, something structured like a cosmic symphony? And what if, on March 17, 2026, at exactly 6:22 UTC, that symphony reaches a moment so precise that it challenges everything we think we know about the universe and about our place inside it? Right now, an interstellar object known as 3I, Atlas, is moving through our solar system. It is not a small comet or an ordinary asteroid. It is estimated to weigh nearly 33 billion tons, a frozen mountain traveling across interstellar space for millions, possibly billions, of years. But the truly unsettling part isn't its size, it's its destination. Because according to multiple orbital simulations, this object is not wandering randomly through our solar system. Its trajectory appears to be guiding it toward one specific location, Ganymede, the largest moon of Jupiter. At first glance, that might not sound remarkable. After all, our solar system is full of moons and planets. But Ganymede is different. It is the only moon in the entire solar system known to possess both a magnetic field and an atmosphere containing molecular oxygen. In other words, it is one of the most biologically interesting environments beyond Earth. And the numbers surrounding this encounter are difficult to dismiss as coincidence. In astrophysics, there is a concept known as the Hill radius. This defines the region around a planet where its gravitational influence dominates over the pull of the Sun. For Jupiter, this region extends about 53 million kilometers into space. Anything crossing that invisible boundary effectively enters Jupiter's gravitational territory. When astronomers performed forensic calculations on the trajectory of 3I, Atlas, back in November 2025, they discovered something extraordinary. The object is predicted to cross Jupiter's Hill radius on March 16, 2026. But it doesn't just cross that boundary roughly, it reaches it with astonishing precision. After traveling trillions of kilometers across the darkness between stars, the projected approach aligns with Jupiter's Hill boundary within only about 57 kilometers. In probability terms, that level of accuracy is extraordinary. It is comparable to threading a needle across the width of the solar system. For many scientists, this precision raises uncomfortable questions about whether the trajectory is entirely natural. If we apply the thinking popularized by theoretical physicist Michio Kaku, this level of guidance begins to resemble the type of navigation a highly advanced civilization might perform when sending an interstellar probe. But if something or someone was guiding this object, the obvious question becomes, why aim for Ganymede? To understand that possibility, we need to examine the moon itself. Ganymede is a strange world. According to conventional planetary science, a moon of its size should have cooled billions of years ago, leaving behind a solid interior. But observations from the spacecraft, Galileo spacecraft, revealed something unexpected. Beneath its icy crust lies a liquid metallic core made primarily of iron. That core generates a magnetic field, creating a miniature magnetosphere around the moon. It's the only moon known to do this. And that magnetic field protects Ganymede from the intense radiation trapped within Jupiter's massive magnetic environment. Because of that shield, Ganymede's polar regions display glowing auroras, curtains of light circling its poles. These auroras were later confirmed in more detail by NASA's Juno spacecraft, which continues to study Jupiter and its moons today. From a physics perspective, these auroras are created when charged particles slam into the atmosphere and are redirected by magnetic fields. But from another perspective, they reveal something equally important. Ganymede has a protective environment. And that environment includes something extremely rare beyond Earth: oxygen. Both the Hubble Space Telescope and earlier missions detected molecular oxygen and ozone in Ganymede's thin atmosphere. The standard explanation is a process called radiolysis. High-energy particles from Jupiter strike the icy surface, splitting water molecules into hydrogen and oxygen. Yet there is an interesting parallel with our own planet. On Earth, large amounts of oxygen in the atmosphere are maintained by life itself. Biological processes continuously replenish it faster than chemical reactions can remove it. That raises a provocative possibility. If oxygen on Ganymede is being replenished faster than radiation alone can produce it, then something else could be contributing. Meanwhile, the chemistry of 3I, Atlas is becoming even more intriguing. Observations by the James Webb Space Telescope detected methane in concentrations 11 times higher than typical comets within our solar system. Alongside that methane, scientists also identified carbonyl sulfide, a molecule that, on Earth, is most often produced by sulfur metabolizing bacteria. Even more puzzling is the object's carbon isotopic ratio. Measurements suggest the carbon 1,3 abundance is roughly 1.7 times higher than the average solar value. In geochemistry, such isotopic patterns can appear when biological systems preferentially process lighter carbon atoms. Taken together, these signals suggest that 3I, Atlas may not simply be a frozen rock drifting through space. It may be carrying complex organic chemistry, possibly even the building blocks of life. Some theoretical models now describe the object as a potential interstellar seeding vessel. Beneath a 15-meter thick crust altered by cosmic radiation, jets erupt into space in symmetrical patterns, releasing material that has remained frozen for unimaginable lengths of time. Officially, NASA has dismissed the idea that the object is targeting Ganymede. The agency has emphasized the importance of maintaining the primary mission of the spacecraft currently studying Jupiter. But orbital simulations suggest something interesting. The spacecraft, Juno spacecraft, still has enough remaining fuel for a maneuver known as a delta-v adjustment. With a velocity change of roughly 2.6 kilometers per second, it could potentially approach within 27 million kilometers of 3I, Atlas. In orbital mechanics, such a maneuver would allow much closer observation of the object's behavior. Yet NASA has chosen not to perform that maneuver, and that decision raises an uncomfortable possibility. If 3I, Atlas truly carries biological material, and if fragments from it were to reach Ganymede's vast subsurface ocean, an ocean believed to be deeper than all of Earth's oceans combined, then humanity could be witnessing something extraordinary. Not the discovery of alien life, but the delivery of it. And as March 17th approaches, the mathematics of the encounter continues to point toward a moment that could redefine our understanding of life in the universe. Because if the numbers are correct, the cosmic symphony is about to reach its loudest note yet, and it's aimed directly at Jupiter's most mysterious moon. And that's exactly where the real story begins. And that is exactly where the silence surrounding this event becomes difficult to ignore. Because to understand why the possibility of a rendezvous between 3I, Atlas, and Ganymede is so unsettling, we have to examine something fundamental about physics itself, the second law of thermodynamics. In simple terms, this law tells us that natural systems tend to move toward disorder. Energy spreads out, structures break down, and over time, everything drifts toward equilibrium, unless an external source of energy keeps things organized. It is one of the most reliable principles in science, yet when scientists examine Ganymede's atmosphere, they see a situation that appears strangely resistant to that rule. Under normal circumstances, a small moon with a thin atmosphere should eventually reach chemical balance. Reactive gases should combine with surface materials and disappear over time. Oxygen, in particular, is extremely reactive. It bonds easily with minerals, ice, and carbon compounds. Given enough time, free oxygen should vanish. But the observations collected by the Galileo spacecraft and later confirmed by the Hubble Space Telescope reveal something unexpected. Ganymede still maintains detectable amounts of molecular oxygen and ozone in its atmosphere. The official explanation remains radiolysis. This occurs when powerful radiation splits water molecules in the ice. Jupiter's radiation belts are incredibly intense, thousands of times stronger than those surrounding Earth. When those energetic particles strike the frozen surface, they break apart water into hydrogen and oxygen. The lighter hydrogen escapes into space, while oxygen lingers behind. It is a reasonable explanation, but it comes with an important limitation. Radiolysis should produce oxygen at a predictable rate. If observations ever show that the oxygen level exceeds what radiation alone can generate, then something else must be replenishing it. On Earth, that something else is life. Billions of years ago, our planet experienced what scientists call the Great Oxygenation Event. Tiny microorganisms known as cyanobacteria began releasing oxygen through photosynthesis. Over time, Their activity filled the atmosphere with O2 faster than geological processes could remove it. Now imagine a similar situation on Ganymede. Beneath its icy crust, estimated to be around 95 miles thick, lies a massive ocean of liquid water. Many models suggest that this ocean may contain more water than all of Earth's oceans combined. Protected from radiation by ice above and magnetic shielding around the moon, it could provide one of the most stable habitats in the solar system. If even simple microbial life existed there, it might slowly influence the moon's chemistry. And that possibility becomes far more intriguing when we return to the chemistry of 3I Atlas. Spectroscopic observations have revealed a chemical inventory that appears unusually rich for a typical comet. Instruments associated with the James Webb Space Telescope detected methane levels far higher than those found in most solar system comets. Methane alone is not proof of biology. It can form through geological processes, but its abundance still raises questions. Even more interesting is the detection of hydrogen cyanide. Hydrogen cyanide may sound dangerous, but in the chemistry of life, it plays a surprisingly important role. In prebiotic chemistry, HCN is one of the fundamental building blocks used to create amino acids and nucleic acids, the molecular components that form proteins and genetic material. Observations made by the James Clerk Maxwell Telescope estimate that 3I Atlas is releasing hydrogen cyanide at rates reaching roughly 4.5 times 10 to the power of 25 molecules per second. That production rate is significantly higher than what scientists usually observe in comets originating within our solar system. When methane, hydrogen cyanide, and carbonyl sulfide appear together in the same object, they form a chemical combination that many researchers associate with prebiotic chemistry, the type of environment where life's building blocks can form naturally. In other words, the chemistry of this object looks less like random debris and more like a toolkit. And when scientists begin to analyze the isotopic structure of its gases, the picture becomes even stranger. Measurements suggest that the carbon released by 3I Atlas contains a carbon-1,3 enrichment, roughly 1.7 times greater than the typical solar ratio. In chemistry, isotopes are atoms of the same element with different numbers of neutrons. Carbon-1,2 is lighter than carbon-1,3, and living organisms tend to favor the lighter version because it requires less energy to process during metabolic reactions. As a result, biological systems often leave behind a characteristic isotopic signature. They consume more carbon-1,2, leaving relatively more carbon-1,3 behind in surrounding materials. When scientists see unusual carbon isotope ratios, they sometimes interpret them as evidence that biological processes may have occurred somewhere in the past. That doesn't necessarily mean life is currently active inside 3I Atlas, but it does suggest that the materials within it may have once passed through a biological environment, or at least through chemistry, strongly associated with life. Now consider the timing. If this object truly carries organic molecules, and if fragments from it were released while passing through Jupiter's gravitational domain, then those fragments would not need engines to reach nearby moons. Orbital mechanics alone could guide them. Jupiter's immense gravity acts like a slingshot. Objects entering its gravitational field can be redirected and slowed through gravitational interactions. Even small fragments separating from a larger body could eventually find themselves captured in orbit around the giant planet. And among all of Jupiter's moons, one stands out as the most interesting destination: Ganymede. The geophysicist Stephen Burns has described Ganymede as something of a logistical hub within the Jovian system. Its relatively low surface gravity, only about 14% of Earth's, makes launching spacecraft easier than from most planets. At the same time, its magnetic field offers protection from radiation that most other moons cannot provide. For any advanced civilization exploring or monitoring a planetary system, such a location would be extremely useful. If we imagine the solar system as a network of gravitational nodes, Ganymede sits at one of the most strategic points in that network. And that is exactly where 3I Atlas appears to be heading. Some models suggest that as the object rotates, completing a full spin roughly every 7 hours, jets of gas erupt from its surface in symmetrical patterns. These jets may be venting material that has remained frozen for millions of years. If even tiny fragments separate during the object's passage near Jupiter's Hill radius, those fragments could gradually spiral toward Ganymede. Over long periods of time, some of them could strike the icy surface. From there, the story becomes even more remarkable, because Ganymede's crust is not a perfectly static shell of ice. Geological evidence suggests it may slowly recycle surface material downward into the ocean below through processes similar to tectonic subduction, which means that anything landing on the surface today could eventually sink into the hidden ocean beneath. And if those fragments carry complex organic chemistry or even dormant microbial life, the consequences would be profound. It would mean that our solar system might not be developing life independently. Instead, it might be receiving it. And as the projected encounter on March 17th grows closer, the possibility that we are witnessing an act of interstellar seeding becomes harder for some scientists to dismiss. Because if the chemistry is real and the trajectory is accurate, then 3I, Atlas, may not simply be visiting our solar system. It may be delivering something to it. And that possibility leads directly to the most unsettling phase of this entire investigation. Because when the clock reaches 6:22 UTC on March 17, 2026, 3I, Atlas will cross directly into the orbital region of Ganymede. This moment is not simply another waypoint along its journey through the solar system. According to orbital models, it represents a very precise intersection, an alignment between a 33 billion-ton interstellar object and the only oxygen-bearing moon in the Jovian system. To understand why this moment matters so much, we have to look at the rules scientists follow when exploring other worlds. In planetary science, there is an international framework designed to protect potential life beyond Earth. These rules are established by the organization known as COSPAR, the Committee on Space Research. Their planetary protection guidelines categorize missions according to the risk of biological contamination. Moons like Ganymede and Europa fall into the most sensitive classification, Category 5. This category exists because these worlds possess subsurface oceans where life could potentially survive. If humanity sends a spacecraft to such a location, that spacecraft must undergo extreme sterilization. Engineers reduce the probability of carrying a single Earth microbe to less than 1 in 10,000. The reason is simple. If we contaminate another world with Earth life, we might never know whether the life we discover there originated naturally or was accidentally introduced by us. But there is one major problem in this situation. 3I. Atlas is not a spacecraft built by NASA or any space agency on Earth. It is an interstellar object carrying organic molecules that are already venting into space. If the observations are accurate, it is releasing methane, hydrogen cyanide, and carbonyl sulfide directly into the Jovian system. Those molecules are not just random chemicals. In the context of biology, they are part of the toolkit used to construct life. In other words, while humanity carefully sterilizes its probes to avoid contaminating alien oceans, a massive object from another star system may already be delivering organic material to one of those oceans. Some researchers studying the isotopic composition of the gases believe the object may even carry a kind of chemical signature. As mentioned earlier, the carbon dioxide detected in its emissions shows a carbon-13 enrichment about 1.7 times higher than the solar average. In isotope geochemistry, that type of fractionation often occurs when biological systems process lighter carbon atoms and leave heavier ones behind. If fragments of 3I, Atlas eventually interact with Ganymede's atmosphere, which contains molecular oxygen confirmed by the Hubble Space Telescope, those molecules could undergo photochemical reactions under ultraviolet light. Over time, they would settle onto the icy surface, and from there, gravity and geology could take over. Ganymede's crust, estimated to be nearly 95 miles thick, is not completely static. Geological evidence suggests that sections of ice slowly shift and fracture. Through processes similar to subduction on Earth, surface materials can gradually migrate downward into the deeper layers of the Moon. Beneath that crust lies the enormous subsurface ocean, believed to extend roughly 60 miles deep. If organic compounds or even dormant microbial structures reach that ocean, they would suddenly find themselves in a stable liquid environment, protected from radiation. At that point, the chemistry of life would no longer be impossible. It would be inevitable. The dynamics of Jupiter's gravity make this scenario even more plausible. When objects pass close to a giant planet, they can experience gravitational assists that alter their velocity. A fragment separating from 3I, Atlas, near Jupiter's Hill radius, might not need propulsion to reach Ganymede. The natural choreography of orbital mechanics could gradually guide it there. Scientists often refer to this cosmic choreography as the music of the spheres. It describes the elegant mathematical relationships governing planetary motion. And in this case, that music may be orchestrating something extraordinary. Perhaps the most puzzling aspect of the entire situation is the response, or lack of response, from the space agencies capable of observing it closely. The Juno spacecraft remains active in the Jovian system. According to mission analyses, it still possesses enough fuel for a maneuver that could bring it closer to the object. Such a maneuver would allow high-resolution observations that might clarify whether fragments are separating from 3I, Atlas, or whether the jets observed on its surface are natural outgassing, yet no such maneuver has been announced. Official explanations point to mission priorities and fuel limitations, but some analysts believe the situation may involve deeper concerns. If a spacecraft were to capture clear evidence that the object was behaving in a non-natural way, releasing fragments intentionally or performing controlled thrust events, the implications would be enormous. It could trigger the post-detection protocols established by international organizations for the discovery of extraterrestrial intelligence. For now, silence remains the safest option. But silence does not change the mathematics. Looking ahead, another spacecraft may eventually reveal the truth. The European Space Agency's JUICE mission, is scheduled to arrive in the Jovian system in 2031. Once there, it will enter orbit around Ganymede and begin mapping the Moon's surface with unprecedented precision. Using ultraviolet spectrographs and visible light cameras, JUICE will analyze the composition of the ice. If it detects organic compounds enriched in carbon, 1,3, the same isotopic pattern observed in the gases from 3I, Atlas, it would suggest that those molecules were delivered from outside the solar system. That discovery would transform our understanding of biology in the cosmos. It would mean life in our solar system might not have developed entirely on its own. Instead, it may have been influenced or even initiated by material traveling between the stars. As 3I, Atlas completes another rotation roughly every 7 hours, it continues its journey past Jupiter. Whether it releases fragments or simply passes through, the encounter will leave behind a trail of chemical clues that scientists will study for decades. The universe may not be silent after all. It may be quietly exchanging the ingredients of life between distant worlds. And if that is true, then humanity may not be witnessing the arrival of visitors. We may be witnessing the planting of seeds. The numbers, the chemistry, and the trajectory all point to the same possibility. Something crossed the darkness between stars and chose a destination with extraordinary precision. Whether it was guided by physics alone or by something more advanced remains an open question. But one fact is undeniable. A 33 billion-ton object from another star system just knocked on the door of our solar system and aimed directly at the one moon most capable of nurturing life. And if you want to follow the latest discoveries about 3I, Atlas, Ganymede, and the possibility of interstellar life, make sure you subscribe to the channel and stay with us until the next update, because the story of this cosmic encounter may only be beginning.